Hello everyone, now we are going to solve the questions based on the torque method. In the question it is given that for the system shown below, m is equal to 1.5 kilogram. So the mass is given, that is 1.5 kilogram, and the spring stiffness or the spring constant is given. Unit must be checked. Okay, so this is Newton per meter. Okay, now here A is in centimeter, 6 centimeter, where L is 14 centimeter. Taking the rod only, the mass is fixed. Here the mass is going to be fixed as light and stiff. Now there is no mass of this rod is given in the question. This is rod which is massless. So the value of C for the system to be critically damped. This is to be underlined. Critically damped is. Now we have to calculate the value of C. Okay. So we all know that C upon M is equal to 2 zeta omega m. Okay. Since the system is critically damped, and we know that for critically damped system, what is the condition for the critically damped? For the critically damped system, zeta is equal to 1. Okay. So our remaining equations would be C upon 1.5, that is the value of mass, and 2 omega m. Now, what is the value of natural frequency? Since in this question, the spring as well as damper both are attached and having the mass m which is also attached at the end of the rod, so we just have to write down the torque equation. So I'm just going to apply the torque method, okay, in order to find out the natural frequency. So for this we just have to assume that this rod is going to be rotated through an angle theta. If this is going to be rotated through an angle theta, that means I theta double dot would be in opposite directions, as well as the spring will be in opposite directions, that is A, and this length would be theta into A. Okay, this is A into theta, and since we are considering torque, so the torque would be also multiplied with A. And now again we have to consider this damper, this torque of damping force, so it would be C, and this the length is also considered as this arc, so this is A into theta dash. So this is A into theta dash. So just write down the torque equations that we get here. I theta double dot. Directions also you have to also consider. So I theta double dot plus C A theta dot plus K A square theta is equal to 0. Okay, now the equations here we get. We just have to rearrange these equations. So this would be theta double dot plus C by C A upon I theta dash plus A square upon I theta is equal to 0. Now see here, you can see here we just have to write down this formula. So what is the difference between this formula and the formula that we are getting from these equations? The thing which is different is here we just apply C by M. That means the directly mass we are going to consider here. This mass is considered when the system is only a spring mass system. Okay, that means there is no rotation of the system. However, we consider torque method. That means there is a rotation of the rod. Okay, we have considered torque, so that's why we have to consider this mass moment of inertia. Okay, and that means we have to consider this angular acceleration like that. So we just cannot apply this C by M is equal to 2 zeta omega n. The things which is going to be different is that this would be the Ca upon I, and that is Ka square upon I theta. That is the equations. So here I am going to remove this. I just want to explain you how the things get wrong if you directly learn the formula. Okay, so if you learn directly the formula, only the formula that you have know, means you are not able to solve each and every question. Okay, so this is what I'm going to show you. That's why I have written that formula. Now you are able to understand. Only to learn the formula is not sufficient to solve the questions. You just have to write down the equations when you apply the torque method. So here you can see this would be the natural frequency. Okay, so the natural frequency would be this, and this is omega n square. So when you apply this, omega n is equal to under root of a square upon I. Now what is I? Basically I, only there is a mass n which is going to be attached at the end of the rod, and the rod is massless. So only the moment of inertia of small m mass is going to be considered. So I is equal to m. This is total length L square. Okay, and we will put the values at the end, but we just have to write down the general equations. This is omega n. From here we can get the value of omega n. Now if you compare these equations with these general equations, that is plus capital C, I am going to consider theta dot upon I plus a square theta upon I. So here you can see this C would be considered as CA. Okay, this is the general equations. If you're not able to understand, let us assume that it is omega n square theta. Now you can see here, this is the general equations. Okay, let us write it as, this is the general equation. So this capital C would be equal to CA. Okay, so that means our formula would be CA upon I, that is equal to 2 zeta omega n. Now zeta is equal to 1 for critically damped system. This would become CA upon I is equal to 2. Omega n is Ka square upon I. Ka square upon I. So when you rearrange these equations, we have to find out the value of C, that is 2 by A under root of Ki A square. So when you consider this A square and this under root, when you take outside this A square, it will be A. Outside this under root, so you will get A, and this would be cancelled out. So finally you will get C is equal to 2 under root of Ki, and the value of I we can calculate here. I is equal to ml square, and n is 1.5 and L is 14. That means 0.14 square. So it would be 0.0294 kilogram into meter square. Okay, so you just have to put this value in these equations. 2 under root of K is 4900 multiply 0.0294, and when you solve this you will get the answer, and you will get 24 Newton second per meter. Okay, so this would be the answer. That means the value of C you will get here, that is 24 Newton second per meter. So I hope you will understand the solution of that question. Okay,